Good morning. Today, I, Rashi Suslati, on behalf of the top coders, take great pleasure in welcoming you all to TCX. Now, what is TCX? TCX is Top Coders' monthly online conference designed by the Student Club for the students that would be showcasing a variety of key speakers from across the globe over a variety of technical domains. Now, I'd like to cordially welcome Mr. Shreyansh Daftry to TCX. Shreyansh is a researcher, technologist, and consultant in the fields of artificial intelligence and space technology. He is interested in pushing the boundaries of technology with innovation in the fields of computer vision, machine learning, and autonomous robotics. His lifelong ambition is to promote both the exploration of space and improvement of sustainable living on Earth. And today, he'll talk to us about his journey to NASA and how AI is being used in the Mars 2020 Perseverance rover. I'd like for you to take on from here, Shreyansh.
So today I'll be talking to you about some of the work I do, which is mostly centered around AI in space exploration, giving examples of some of the work I've done and how it's being used for the recent Mars rovers, and also an outlook on how some of the work I've been doing in artificial intelligence that will be held for future exploration that hopefully some of you who are interested in space can also contribute to. And during that part, I'll try to briefly touch on on my lessons learned as well as my journey through all of this. But a lot of part of that, I'll leave it in the end for question and answer, where I'll be happy to answer your questions regarding any part, either about the work or about my journey and career in general. So let's get started. So with the basics first, what's artificial intelligence? Assuming some of you at least are familiar with with this terminology, or at least have been hearing it in the while, and it's really hard to not hear the word or the buzzword of AI these days. How I like to define AI at a very broad term is it's a collective term for any computer system that can sense the environment and intelligently think, learn, and take action corresponding to that. A famous quote that I really like is this: "AI is the new electricity," by one of my favorite professors in AI, Professor Andrew from Stanford University. And this is really how I personally also believe the word AI is being captured right now. Just like AI, just like electricity, pretty much impacted every single industry and how human lives existed a century back. It's basically AI is trying to do the same today, and hopefully for the next few decades as we move forward. So what is this hype about AI, and why is this suddenly growing exponentially? And everywhere you pretty much see everything that you want to buy on the internet, you see the word AI with it, and that, hey, this is AI powered, and it just makes it, at least it's claimed to make it 10 times better. So as it turns out, it's not something that's absolutely new. It's been something people have been studying and thinking about for several decades already. It used to be called artificial intelligence as a whole, but now in recent times, there's been more of development of what we call machine learning and deep learning. And I'll briefly touch on what that really means. So how we used to do programming, and this is Top Coders event. I'm assuming all of you are at least familiar with programming to some extent, or at least getting started with that. So if you're told to do programming, our classic way of doing that is, given a problem, we basically write these lines of code, which are usually translated from rules of if and else conditions, or certain things we know about the problem, and we try to basically write down these big pieces of code together to solve our problem. That's how we do it. But what if you don't know the rules? What if you don't know how to write that piece of code? And a classic example of that is playing chess. And this is so the game of chess is so complex that if you start writing down the rules, trying to teach a computer how to play that, it becomes so large that it's almost an intractable problem where you just cannot write down possibly imagine or enumerate all possible conditions that might exist in this. And this is something that has been perplexing coders, let's say, or artificial intelligence or computer science developers for several decades. It had been for a while, till 1997, or at least till the starting since then. And a major change was happening around that time. And one of the change was that rather than having this paradigm of writing down programs, we were shifting to this technology of machine learning, where, and in the most simplest term, the major change that we have here is that rather than trying to tell the computer how to program or get by how sorry telling rather than trying to tell the computer how to perform an action by using a program, we give the computer a set of data or experience through uh, basically through past actions that have been done on the same problem. And we tell the computer that you tell us what should be the code or what should be the model, and there could be a lot of different ways to define how you define this code or the program. So this has been the real paradigm shift in how we think about coding. And this is the field of machine learning uh, in a very nutshell. And to think of it, this is also how humans learn. When we are growing up, while we do go to school and we learn certain basics about a lot of things, fundamental rules about how things are happen, a lot of things that you usually do, like for example, if I ask you to walk out of the room, you would not really know the exact mathematical model of how you would pick yourself up, walk down the street, or go out of your room, and how would you be navigating that path. You just do it because you've been so well trained by experience to do it that you don't really know how to model that or the code for that. You just know how to do it. And this is really learning, trying to bring this kind of experience-based action into your programs or into your code is what's the field of machine learning. Also, if any of you have any questions, please uh, please write down in the chat. And if it's something that's critical that maybe will help everybody understand something that I'm presenting better, maybe one of the moderators can interrupt me rather than everybody trying to moderate interrupt in between. But yeah, feel free to interrupt me if you think that will help you understand better. Okay, so moving forward, so when we talk about AI as a revolution, it's not just something in the future. It's something that's already happening around you. Pretty much a lot of the things around you, you may or may not know it, but is already using a lot of AI. Netflix is a great example. It basically the recommendations that you see of what movie you should be watching next comes directly because of AI algorithms that are being built. A lot of the Wall Street financial data and market predictions basically use this kind of AI time series predictions. So, and another great example in a household would be Alexa. Uh, the way you can naturally talk to Alexa as you would talk to another person is also coming from a subfield of AI called natural language processing. What I do. So basically what I do within AI is a subfield of what's called computer vision. And computer vision is basically, in a nutshell, trying to teach computers how to see. Humans get most 80% of their sensing from their eyes. We have other sensors like ears, nose, touch, but still a lot of what we learn and what we do is based on what we see. And this also is kind of ironic because this makes it one of the most difficult challenges for AI. And the reason for that is we just don't understand how we see. There is still a lot of contradictions in neuroscientists. Uh, there in developing concrete theories regarding how we interpret things. What we see, and this is the same problem that computers face. What we see, what a computer, when you send it an image, is basically a huge number of zeros and ones, like you see on the left here. But how do we make sense out of that is something that we don't really have good models for. And this is what the task of computer vision is. And this has made a lot of progress in the last 5 to 7 years. And some examples of this is what you'd be seeing in your iPhone when you try to do facial recognition. It basically uses AI and computer vision to detect where your faces are, and not just where those faces are, but who it is. So it pretty much can now tag yourself, and it does that through past experience of looking at the features of your face. And these kinds of technologies, what I do is I try to develop this for robotic application. So a quick snapshot of my journey. Um, so I'm born and brought up in Calcutta, India, and then I did my undergraduate degree in electrical and computer engineering from Manipal, Institute of Technology in Manipal, not far from where you guys are in Bangalore. After I graduated with my undergrad degree, I went on to spend a couple of years in Austria in a university lab in Graz. And it was It was a computer vision lab where I was trying to work with world-class researchers in computer vision, just trying to get more acquainted with how research is done and getting more in-depth knowledge and experience in the field I wanted to work in. And after that, I moved to the US, where I pursued my master's degree at Carnegie Mellon University in robotics and AI. And after that, I basically straight after that, I joined JPL. Uh, that is basically Jet Propulsion Laboratory, which is NASA's one of the NASA center that works on robotic spacecrafts. And we are based out of Los Angeles in California. A lot of while I was going my while I was in high school, I already had a huge interest in programming, and I think a lot of my current work really stems from my deep interest in problem solving and coding. I think I had started coding in C++ in grade six, and I was always interested in learning more about how to program more complex codes. I used to take part in Olympiads. I used to take part in other competitions, always excited in trying to solve more complex programs. And this eventually led to my interest in robotics and AI, where I was really interested in learning more how do we make these robots intelligent. So throughout my undergraduate degree, what I did was spend a lot of time trying to build robots as well as get more hands-on experience. So this is a snapshot of some of the projects that I had worked on during my bachelor's degree, either through internships or through hobby projects. Actually, most of this work here that are through internships. And this is definitely a lesson that I've learned is while you can work on a lot of interesting projects in your university, in your lab, it's also good to go out and work in real world problems in other areas with other people who are trying to solve these kinds of things. So just trying to run you through some of this. On the left, you see two projects that I worked on. First during my internship in Austria and then during my full term when I was there for a couple of years, I was trying to use drones and teaching them how to see to build intelligent models that could be used in the architecture and construction industry. Uh, Similar kind of technologies are used to build city scale maps. So kinds of like when you go to Google View or Google Street View, and if you uses that, you see a 3D map of that of your surrounding. A lot of that often can also be captured on a large scale from drones. At the same time, I also had the fortunate experience of interning at Carnegie Mellon during my undergraduate, where I also did a work for I did a NASA project, and this was part of the Google Lunar X Prize, where we were trying to build robots for we were trying to build robots that could explore caves on the moon someday. So having this kind of really interesting experiences and working on real robots, trying to develop AI systems and computer vision systems for them, trying to work with researchers and world leaders from around the world was really a great way to understand if I really like this field, as well as build up your resume, as well as expertise that could eventually help you get into graduate school and other preferred positions in the industry. And again, I'm just giving a snapshot here. I'm happy to talk to you guys about any part of the uh, how should you be approaching your career, how should you be looking for internships or graduate school, etc. at the end through question and answer. So let's get more into now my current work and how, so eventually through all of this work in trying to build better robots, trying to learn different parts of robotics and getting more in-depth expertise in computer vision, I found myself working at NASA. And this was very fortunate because growing up, I had basically two passions. One was trying to build intelligent robots, and the second was space exploration. While I did not really pursue a formal degree in aerospace engineering. Uh, NASA and Jet Propulsion Laboratory, where I currently work, is probably the only place in the world where I could pursue both robotics and space exploration together. So that was very fortunate, and I was very lucky to get that position today. And my role today is to really look at how technologies like AI and robotics can impact the next few decades of space exploration for NASA and uh, globally as a whole. So you would ask, why do we even need AI for space exploration? And that was one of the first questions I had to start thinking about more deeply after I joined. So NASA, as you might know, has been exploring the whole solar system for almost 7 decades. we have been building great machines, really powerful spacecrafts, and really great capable spacecraft that have been to almost all the parts of the solar system. Different target bodies, like from the moon Mars to outer planets like moons of Jupiter, as well as visiting Saturn, Neptune, and Uranus. Two spacecrafts here that you see on the right illustrations are from Voyager 1 and Voyager 2. These are, in my opinion, an exemplification of some of the greatest machines humans have ever built. These two spacecrafts were built in 1973. I think they were launched in 1973 uh, from, and they were built at Jet Propulsion Laboratory, and they basically were made. Uh, they had a certain they had a certain mission which only lasted a few years, but they are still active today, even after 40 years, and they're still exploring not just our solar system. They've already crossed the solar system and are the only man-made objects to be exploring interstellar space today. So as we talk, both the Voyager 1 and Voyager 2 spacecrafts are right now in interstellar space and still going further and further away from us and talking to us and sending signals and science back to us. So the summary is we built some really good machines. But when I started to when I as a roboticist start to think about this, when with the interest of can these spacecraft do things intelligently, uh, then I start to question maybe these spacecrafts are not really intelligent the way I like to define it, or how we use AI or artificial intelligence in the current uh, time. These are two great pictures that I really like. On the left is a picture from the Apollo missions during one of the first landings on the moon. So one of the key things that allowed us to get to the moon was the sheer intelligence of the human astronauts themselves, who were able to perform the most difficult part of the mission, which is landing. And till date, no spacecraft is really capable of trying to do these kinds of landing in the same way a human could with that kind of pilotage uh, and the dexterity that's required for that. On the right, you see the Mars rover Curiosity, which is right now on Mars as we talk. It has probably given us more science return and told us more about the solar system than any other spacecraft built. And in order to operate that rover, while it's not entirely manual, it can do certain actions on its own. It still has a team of almost 100 people sitting in the spacecraft operation facility, the mission operation facility, as shown in the picture below, uh, where it's constantly being communicated. And at the beginning of every day, we send it a plan as well as other instructions on what to do and how to do those things. So these objects, while they've done great things for us, they are really not really intelligent. And what we need in the next few decades is really AI to empower these spacecraft to be independent on their own. So why do we need them to be any different? We've done great so far. And one major reason, actually there are two major reasons. And one of them is first communication. Uh, when we And this is basically, if you imagine when you're sending a signal from here to Mars or to some of the places, Moon, Mars, or beyond, it takes a long time to send that signal just because these objects are so far away from us. If you send a radio signal to the moon, it takes only a few seconds. So if you were trying to basically operate a rover on the moon, you could pretty much joystick it. It would just feel like a delayed internet connection. But if you are now trying to do this on Mars, this would be a problem because uh, it could take almost 20 to 30 minutes, depending on where Mars is with respect to Earth, to send a signal back to Mars. Well, this is okay if you just want to send it a few plans, or if you want to send it instructions that is not safety critical. But let's say your Mars rover is in a problem and it needs to get out of it urgently or immediately, then it cannot really rely on the human to give it or take it out of that danger. It needs to be able to bring itself out of that danger before it's too late. Uh, and this kind of problem becomes even more as we start to go further and further out. Right now, as we talk, one of the highest priority targets for NASA and the global science community is one of Jupiter's moon, Europa. Europa, and the one that is shown in the picture here. And the reason why Europa is so interesting and important is that it is part of what's called the ocean bodies or the ocean worlds. And these are these objects in the outer solar system that have or that are that we believe have water in them, and they are covered with ice. So in the picture, you can see that you can almost visualize that the whole surface of Europa is basically covered in thick layer of ice. And the scientists believe that underneath this ice are deep oceans, just like here on Earth, when you imagine places like the Arctic and the Antarctic. And where we find water, we have a high probability of finding life. So one of our highest priority missions in this and the next decade is basically to send a spacecraft that could go to Europa, go to those oceans, and really try to find a sign of life for us. Now, when you imagine how far that is, it could basically take hours to send a signal to Europa and come back. And this is a problem because we just cannot operate the way we have been doing for the last 6 to 7 decades. We need any spacecraft that goes to Europa or beyond to be autonomous completely. It needs to be able to behave intelligently, act on its own, uh, and do actions without really any human involvement for several hours. The second problem is more just about the scale of economy. On the left, what you see is a picture from already a few years back, which shows all the spacecraft around the Earth's orbit at any given point of time. While when we look up, we don't really see all these spacecraft, but the, um, the, but the space industry has been exponentially growing in the last few years. And the amount of debris and satellites around Earth's orbit is also exponentially growing. And this is a problem. Uh, if you remember, looking back at the last example of the Mars rover and a 100-person team that's connected to it, if you imagine that for each of these assets that's around Earth, if you have a 100-person team trying to operate that, it's almost impossible to have to operate that way. And this problem only gets worse when we start to go further and further out, or when we start to scale up, uh, as you would have to do that for something like a Mars colony. That's the vision of Elon Musk here, and this is a picture from that. It basically now imagine operating these thousands of assets, objects, spacecrafts, rovers, even humans, and if you had hundreds and thousands of people here on Earth trying to basically look after each of those, it's just impossible to work that way. So basically, that makes my job interesting. That now I get to build AI that could help us solve those challenges. In my work, I've been mostly looking at robotic problems. So how could we make uh, into AI technologies that could enable space exploration for robotic missions. There are a lot of other work that goes into that NASA does that doesn't relate to robotic exploration. So, for example, a human mission to Mars also would benefit a lot from AI. So would a lot of Earth science missions around Earth's orbit. But a lot of the work I do is really related to robotic missions to Moon, Mars, and beyond. And I'll be talking about some of the work I do in trying to make those kinds of robotic technologies more uh, intelligent. Within that, I've mostly distilled down some of the key areas in which we work, and those are related to autonomous navigation. How would you, and that relates to how can a Mars rover go from point A to point B, just like self-driving cars do that here on Earth, or at least are trying to do that here on Earth. Science and mission planning. So how could we enable a lot of the planning activities? So right now we send a lot of the activities like, okay, your Mars rover should be doing this and then this and then this. If the Mars rover is told to operate for a month on its own, can it do that kind of planning on its own? Precision landing. So I told you about the importance of trying to land on the surface of and land on another planet on its own, and how humans are really involved with that kind of activity. So trying to do that precision landing on its own is another key capability that would be enable us to have great returns. Manipulation, when we are on Mars or any other planet, we don't want our rovers to just operate or go from A to B. We also want them to do things like pick up a rock, test a rock, create samples, or do microscopy, do some other science experiment. So doing those kinds of things on its own is what we call autonomous manipulation. And finally, looking at far out at human robot teams and how can we enable intelligent robots with AI that could work alongside humans to do great tasks together. In this talk, I'll go briefly into some of these technologies, depending on how much time I have. But yeah, if any of you are interested in things I could not cover, please feel free to reach out to me later. So autonomous navigation. So how do Mars rovers really navigate, uh, uh, how do safely around on the surface of Mars? It primarily uses two modalities of sensing. One is looking at the rover images. So basically it has two sets of cameras called the nav cams and the has cams. Those are basically navigation cameras and hazard cameras, and it uses these cameras to look what's in front of it, just like humans do with their eyes. We also use to orbital imagery, like seen on the right here, to plan out paths. And this is really what humans also use to plan out paths right now. That hey, in front of you there's a big rock, try to go from here. And on the right, you see this more from a global scale, that there are these sand dunes in front of you. And this is shown by this picture here, that you can see that humans, when they look at these kinds of images, we can very naturally just say what kind of terrain it is. Even if you all have never seen an image of Mars, if I show these pictures to you, just based on your experience of looking at images of Earth, you would have some idea. And I'm confident that a lot of you, even if you won't know the exact terminology, you would know where sand is and where rock is. And if I give you the controls for a Mars rover, you'll basically be able to somehow manage to navigate it safely around this planet. So humans are really good at this. And the same thing is on a global scale. We can basically look at these things. These are sand dunes. These are areas we don't want to go. Um, but this is something that the Mars rover cannot do right now. Mars rover basically, it does some form of hazard avoidance, but it does this in what I like to call as in a geometric way. So it basically looks at, there is an obstacle in front of you. So there is a big rock in front of it, and there is a mountain in front of it, and these kinds of geometric obstacles, and it tries to basically navigate itself around. So this is how the Mars rover currently sees the world. But there is a problem with this, that the world is not just geometric, uh, and there is a lot of semantics in the world. So for example, one of the biggest challenges that the Mars rover has encountered in the last 2 decades is sand. And we've already lost rovers that have been stuck on sand. And this is a video of the Curiosity rover where it was stuck in sand. It took engineers here on Earth almost 6 months to engineer a way to basically get these Mars rovers out of sand. Otherwise, we would have basically lost the spacecraft and the mission. And we've already had this kind of problem where we actually did lose the Spirit rover and we could never recover it. So this is a major problem, and doing the kind of geometric reasoning we have been doing on Mars rovers does not allow us to avoid these kinds of sand traps. So in response to this, one of the technologies that I have helped contribute to in the last few years is using machine learning and deep learning to basically build a terrain classifier that's basically saying, teaching these robots, teaching the Mars rover to do this kind of reasoning that, hey, there is a mud in front of us. Or there is, like, if it was on Earth, you would say, there is a water patch. So for example, when you're walking on the street, you would not go into a muddy area and you try to take a more paved area. So this is the same kind of technologies that we are trying to build for the Mars rover, and we call it terrain classification. And we do this through learning from data. And just to show you here, going back on the slide, sorry, is the different kinds of classes of terrain that we use. So when we are on the ground, with the ground images, we have a set of 6 labels that we use to classify different terrains, but we use a much more finer grain classification with almost 17 labels when we classify this from the orbit. And we're using basically a lot of the great technologies that are being built here on Earth already. There is tremendous development happening all across the industries, especially in the area of computer vision. So we work with those people, we work with Google, we work with a lot of other industry partners to try to leverage the kind of work they are doing and trying to then adapt this for the kind of space application problem that we have. So the way we train our models for trying to do terrain classification on Mars is we look at these Mars images and we basically label those with different kinds of terrains. And then when the Mars rover sees them, it tries to predict it on its own on what those terrains are. And this is a very standard way of doing machine learning and deep learning. Now, there are three key challenges that we have to face on the Mars for the Mars rover application and space exploration in general that you typically don't face for when you're trying to build AI technologies for here on Earth. One is availability of data. So unlike for a lot of problems here on Earth, we just don't have data. If you're trying to solve this kind of what's it called here on Earth, a semantic segmentation problem, or trying to do an image classification problem here on Earth, you could find data sets with millions and millions of images that could work. But we don't just don't have that for Mars, and we cannot find that build that kind of data sets because we only have geologists. uh, you basically around the world you have 10 or 12 people who understand this kind of data and who can do that work for us, and as you would understand they are extremely busy people, and trying to find time to help ask them to basically label images for us is almost an impossible task. So what we did was we went out and started a citizen science project called AI for Mars. And this is open to both. This is still running, and we actually had a great campaign over the last few months. Um, and the simple idea here is that while geologists are great domain experts who know how to do this very accurately, humans, like all of us, you and I, we also, even when we look at these images, we roughly can interpret them just because the human brain is so powerful and capable. We know how to, if somebody tells us how to do this, we can do this easily. And this is the whole concept of citizen science that's really growing in trying to make everyday citizen to contribute to science that was typically thought to have been capable only by people who have PhDs and tens of years of experience. So we took this simple idea and we went out and we basically created this platform called AI for Mars, where you could look at images, and basically you'll first go through a tutorial that have been developed by geologists to tell you how to label these images in a very easy way. So basically by spending 10 minutes understanding that tutorial, you're now ready to help us build AI for Mars. Um, there should have been a link here, but it's missing, but I'm happy to send it into the chat later. But if any of you are interested in helping contribute to this, you can basically go, even Google AI for Mars, go to the pages, help us label images, and basically be part of the AI development that basically helps the rovers on Mars navigate better. So yeah, so that solved the data problem. So we were able to get, I mean, that was one of the solutions for the data problem, that just in less than 3 months, we were able to get almost 300,000 labels for our problem. And the best part was these labels came from everyone. So we had uh, kids who were basically in third grade label these for us while they were sitting at home during COVID, as well as you had senior citizens who were labeling this for us. And from all around the world, we basically have this tutorials translated in 20 plus languages, I think. And yeah, so basically in any language you can do help us, and this was really a great way to collect new data and build AI models for space exploration. Another more structured way that we use is basically in the field of graphic design and game design. So if some of you are interested in developing games, you would have realized that recently the those game engines use are extremely photorealistic. And this is the kind of technology we are using, and we are working with those kinds of game engine startups and game engine technologies to develop these uh, a similar thing for space, for Mars, where these things are already auto labeled. So then we don't need people to actually label each of those pixels, which is a very cumbersome job. We basically run this all the Mars images through a game engine, and it basically tells us which part of the pixel is which, and it gives us this kind of training data that can be then used to train these deep learning models. And this is a video of, I'll let this video play basically of the kind of results we got and labels showing on a time lapse of Curiosity rover. So on the left again is an orbital image, and on the right is the actual images that the Mars rover saw while it was moving and operating on Mars over, I think this is over a period of several months. You can see the day passed by. Sol is basically a Martian day, which is just over which is I think like 30 minutes more than a regular Earth day. And this is the predictions coming out of our machine learning AI tool trying to label, now basically saying which part of the surface is what, which is then used by the Mars rover to navigate itself more safely. Another challenge that we have for Mars rover is computation. If some of you are familiar with machine learning, one thing you would know is these are very compute intensive. They require gigantic GPUs, which are very power hungry. Um, in contrast to that, what we have on Mars is basically the computer on running on the Mars rover has the same compute, which is 1,000th that of your phone. So it's pretty much, think of a computer capability from the 80s, and that's what the Mars rover is currently running. So this is a challenge for when you're writing code, and as a coding community now, or programming community, when you're tasked to do programming for a computer like that, you have to think about intelligent ways of how can you build great capabilities in extremely efficient compute ways, which can run almost negligible power and negligible energy consumption and still perform to a level which is capable by really efficient model. And this is the kind of thing that we've built here on, we've been trying to build, and it's what we call it is Spock Light, which is a light version of the terrain classification that only tries to do sand versus no sand, and then uses it for navigation purposes, just like you saw in this video right now. The third major challenge that we have in deploying these for space exploration is testing. What you see here in the picture is a surrogate rover that we developed in, and a surrogate environment that we have in JPL, what we call the Mars Yard. And what we do here in the Mars Yard is basically create environments which would be extremely similar to what you would observe on Mars. Now, you of course cannot create the radiation environment or the same kind of sunlight, but we at least try to create the same kind of terrain properties. We create a rock distribution so that when the Mars rover is moving, it encounters the same kind of geometric and uh, semantic obstacles that it would encounter on Mars. We try to replicate as many things as possible, and test out each of those things so that we don't get surprises when we go to Mars. We also have other experiment areas where we have chambers where we can replicate the thermal condition and the vacuum, as well as the radiation environments to test those parts. Another great thing that we worked on is basically taking this kind of terrain classification that we were doing with orbital imagery and trying to build something like what we call the Google map for Mars. Now that we know where the Mars rover can traverse safely and not you basically can do the same thing that Google Map does, and if you basically ask it to go from point A to point B, and this is the same thing now, almost the same thing that Mars rover can now do. Now, let's say it wants to go here, it basically will try to call this tool and basically ask, okay, what is the best path for me to get there? And then it'll, over tens of kilometers, it'll basically try to take that route as it's going from there. So yeah, this is another great example of the kind of AI, things that AI is enabling for future exploration. And we've been incorporating this kind of tool in the Mars 2020 rover. And this is the illustration of the Mars 2020 rover and the different instruments that it'll be carrying for it. It is the most powerful rover, most capable rover that we have ever sent to Mars. And it's really going to be helping us shape a lot of shape and answer a lot of the major questions that humanity that are the biggest open questions right now that NASA is seeking, and they basically get distilled to four major goals. The first is looking for habitability. So basically answering the question that was there any past environment on Mars that could support life? So was there any past life on Mars? Can we find signatures for that? Basically, can we find a fossil or any other? There are a lot of ways to establish that there was previous life on Mars. So those are what's called biosignatures. So some of these instruments really that are going to be on the rover will help us detect those biosignatures. The third and interesting thing about this rover is that it's not just going to be doing science there, it's going to be collecting samples for us and putting them into small sample tubes and leaving them on the surface of Mars for a future rover that we are currently building to bring that back to Earth. And this is all part of a big campaign called the Mars Sample Return. And this is one of the highest priority missions for Mars from a science perspective for this decade. So the goal for NASA is to bring back pieces of Mars by the end of before the 2030 back to Earth, so that we could study those samples not just using these limited instruments, but by all the labs all around Earth. And the last most important thing I think is to test these, is to basically help pave the way for future human exploration to Mars. And this is also something the Mars 2020 rover will be doing by having an instrument that is going to try to produce oxygen in the Martian atmosphere. This is a picture of the Mars 2020 rover, which is now called Perseverance, from the spacecraft assembly facility at JPL, and this was taken in January this year, right before it was about to be shipped, packaged and shipped to the Kennedy Space Center for launch. So I've been talking mostly about the Mars 2020 rover, but one of my favorite parts about that rover is not the rover at all. It's a small helicopter that's going to be going along with this. As you would have seen in my previous video in a slide, a lot of the work I did during my bachelor's and in Austria growing up for almost 5 years was on aerial robotics. So I had been working a lot on drones and autonomous drones. So this is very exciting to me because this will be the first time ever we will be sending an aerial vehicle or a drone to another planet. So basically, when this is successful, early next year, we would have established that we could actually fly on another planet body. And this was something that was thought of almost impossible for till now, because Mars does not have the same kind of atmosphere that Earth has. It only has the 1% density. So that makes flying on Mars extremely difficult. So the engineers here at JPL had to really rethink how to build these helicopters, and especially to build those for the Martian environment. And this is something that also is powered by AI. This is just an illustration video of how this would look like. So the Mars helicopter would be sitting underneath the belly pan of the Mars rover, and once on the surface of Mars, it will basically be dropping it on the surface of Mars. Once dropped, it will basically be doing a, a few number of sortie flights, which will basically, each sortie will be for around 90 seconds, where it'll be taking off, flying around, creating a map of its environment, and then landing back safely. So the part where it'll be using AI is to navigate itself and land. So as you see now, when it's moving, it's going to be taking images from a camera that points down. It's going to be taking those images, and it's going to be using computer vision to navigate itself and localize itself to where it is on Mars. And then it'll be using that kind of images and AI technology again to landing back safely on the surface of Mars. And yes, the Mars helicopter is called Ingenuity. So both the Mars 2020 rover and the helicopter were launched a few months ago from the Kennedy Space Center. It was a beautiful launch, like you see in the pictures here. As we talk, it's currently on its way to Mars, and it's expected to land sometime in February of 2021. I talked to you about Mars rovers, Mars 2020 rover and the Mars helicopter. And this is a snapshot of not just technologies we've been building for Mars that's going currently, but also looking out for. And that's really where AI, I feel, is very interesting, is especially as we go further and further out, for Europa, like I was telling you before. And if you remember from the picture of Europa, I told you it's an icy body with the ocean underground. So we've been trying to develop robots that could help us get and operate in those kinds of environments. So the picture on the left and the picture on the right, you see are kinds of concepts that we are trying to build for robots that could explore Europa. So on the right, you see a robot that we basically we're trying to build wheels and mobility system that can help us basically walk and navigate itself on ice. And we try to build these robots. We've been doing a lot of testing, and we take it out often to Antarctica, Greenland, Iceland, and other places here on Earth that are very similar to what you would expect. And we try to test our robots in those kinds of environments. On the left is an illustration of a robot that we've been building that's called the Aquasimian, which is the same kind of robot that you see on the right, but that will be more developed for trying to work in deep sea oceans. So this, while we're building this for Europe and other ocean worlds where it can go to those deep sea and try to detect life, these kinds of robots are also helpful back here on Earth with things like search and rescue. The classic case being MH370, where it's lost in an ocean. We could easily send robots like this for search and rescue, as well as for trying to work in areas like oil and gas pipelines and trying to repair those kinds of things. Right now, we do that by using human divers, which is an extremely dangerous thing to do. In the middle is again a similar kind of robot that we call Lemur. It's basically a rock climbing robot. So far for Mars, we've been developing robots that could drive on the surface or hopefully now fly on Mars. But the most interesting signs that the scientists really look for are on the surfaces of mountains and cliffs. And what they really want us to do is go really up close to these cliffs, like a rock climber, and then try to basically use instruments and do science on them. So we've been building this robot called Lemur, which is modeled after a gecko. So it could basically climb vertical surfaces. Um, since I'm running a bit late on time, I'm just going to show a few pictures and then skip to the end. And in order to test the rover called Lemur, we basically took it to a lava tube, which is basically an underground cave, similar to what you'd see on Moon and Mars. On the top right is an example of a lava tube on the Moon that was taken from orbit. And this is very similar to here on Earth in New Mexico in US. And we basically took our robots there to test these kinds of rock climbing technologies. And again, this is powered by AI, and we've been using similar kind of classification technology, computer vision, to help these robots determine where can they really place their foot. So the kind of thing is, if you're a rock climber, you want to make sure that you put your hand in the right place so that you don't fall off, while reasoning about all the physics of your body as well as the interaction with the rock surface. So we're try to teach these robots these kinds of intelligence. Sorry. And this is a video of with a fun background music of the same thing for the test we did in New Mexico. So if some of you are interested, basically what it does is it has the key technology for what allows it to climb is called a microspine gripper. And it's basically the same kind of adhesive technology that a gecko has in its legs. And it basically uses really fine surface tension to basically hook itself onto the surface. Okay, so in the interest of time, I'm gonna skip talking about some of the other things and skip to the last part. Basically saying that we will be, one of the things that I'm most personally excited about is how do we use robots for human missions. And this is something we're now starting to do for Moon right now with, NASA plans to go to the Moon, hopefully by the middle of the 2020s. And we will be sending robots there, and we'll be going there with along commercial companies. So we've been building human robot teams that could operate on the Moon. And once we learn from the Moon, how could we live sustainably on the surface of Moon, we hope to go to Mars soon after that. And that's the kind of technologies I plan to be working in the next few years, hopefully. And this is just fun posters from NASA that says that we're always looking for intelligent people, really excited, passionate people who are interested in helping us develop these kinds of robots, as well as pursue space exploration. So feel if you're interested in joining NASA or interested in following this kind of work, then please reach out to me and we can talk more about it. And I'm happy to take questions now. Thank you.
Shreyansh, we do have a few, we have actually quite a few questions.
Great.
Okay, so the first one is that is it necessary to be doing extra courses, internships in order to get into universities for masters, or would a good GRE score, recommendation letters, and undergraduate GPA be fine?
It depends. So it depends on what's your goal. So if you're looking to do research and pursue in-depth work. So, for example, if you really want to do robotics research or machine learning research, yes, you do. And I'll get to that in a minute. If you just plan, if your goal is more to get an industry job, uh, may or may not be. It's may or may not be, especially for professional courses. You probably don't need any of that. But if you're really looking for in-depth technical research courses, which are more, which are generally more technically, which go in more depth compared to just professional courses, uh, then you would need. And the reason for that is that, especially if you're thinking of top graduate schools, so top 20 rank school, then what would happen is there would be there is a lot of competition, like you would imagine. Uh, so you do have to stand out among them. And if you just have a good GRE score, that's not going to make you stand. So for example, let's say now you are running you're basically think of yourself either as a professor or as somebody who has a company and you want to hire the best talent for yourself. Now, would you hire somebody who has got a A plus in his course, or would you hire somebody who's really done the kind of work you already want to do? And he has a lot of experiences working through other real world projects. So I think it's not just about check mark of internships. It's really, have you done, if I want to pursue robotics and get into if I want to get into Carnegie Mellon, which is the world's best university for robotics, I need to show that I'm not just interested in robotics. I've done an initiative to actually go out of my comfort zone to look for more things than my university provides. So I can pretty much assure you that at least for the top 10 schools, um, I have been on the admission committee and we don't even look at GRE scores. We don't care about your grades if they are beyond a certain number. So if they are really low, you better have an explanation. What you should not have are red flags. So if you have on a scale of 0 to 10, if you have a 6 or a 7 or something below, and those are just subjective numbers. It really can vary depending on which university you're from. But if you are relatively low compared to others, and that stands out, you should have an explanation for that. Everybody may or may not have a bad semester. So, for example, let's say you want to get into machine learning or programming or computer science, then uh, especially for those kinds of degrees, I would look for a strong math background and a strong programming background. So it's okay if you had one C in your course, but I would always look for a reason for that. Okay, why did you? So in your essay, or try to explain it out that, hey, that semester I was either sick, or hey, that semester I was focusing more on an interesting startup idea I was working on, or on a project so I spent more time focusing on that rather than that. But if you consistently have shown that you just cannot do good math or you cannot do good programming, then you just don't match up. So then you're not fit for that degree. I'm not going to look at your overall GRE score after that. Uh, the same thing, let's say it doesn't matter if you're a 10 pointer. I don't care if you can do great in courses if you cannot build something that you're like. This is something that's very famous in the US, especially like we've been on admission committee. You're told to look out for is paper champions, people who have 9.9 on their GPA, but and when they come, they would still do great in grad school because they just know how to master an exam. But when you're given a problem to solve, you cannot do that. So it really so when you're looking at admissions, you look at a holistic thing. We look at everything that you bring to the table. And that includes diversity. That includes, if there are two people who are absolutely great, and then a third person who is a bit less, but he's bringing something really new to the table, I'll go for the third person. So that kind of thing. So top schools really, really give very heavy weightage on that. Uh, Two things which are the most important are recommendation letters and your statement of purpose. The recommendation letters, if you they need to be written by other people. I mean, that's just not even that doesn't even need to be said. And but if you have worked with some good people who they know, so if I'm on the admission committee, and if I have worked with somebody who I know is a world leader, and if he writes your name, that hey, I have worked with this person, he's pretty good, you should consider him, then I'm going to go after his word. So recommendation matters, but it also matters who it comes from.
Great. Now, someone's asked if AI will power this spacecraft, but will we be able to manufacture and run the AI programs? Because the hardware can act as a bottleneck eventually.
Yes, so this is where there are two ways to approach this problem, and we're already working on both of them. As I briefly mentioned, one is that you optimize your software to work on the hardware that you already have. Um, Sometimes, unlike, so this is one thing I've been learning, and still, so when you're trying to learn computer science, when you're in school, you're just given a program, you need to solve the problem, that's it. When you're a computer scientist, even when you're trying to work on a computer science area, you often don't even think about other areas apart from computer science. But when you go beyond that, and when you're going into the real world or for this problem out of this world, uh, you are not just going to work on software. You're going to have to interact with hardware. You have to interact with energy, with power, with radiation. So this is what comes down to system engineer, the field of system engineering. So software and programming is just one part of it. So now you have to think of writing software that can actually fit in the context of this bigger system. So two ways to solve that problem for compute is one, you optimize your software so that it can actually run on those kinds of things. So, and the second is then you optimize hardware that can actually accommodate these kinds of things. And we're working on both of them. We're trying to look at how can we build better, more efficient FPGAs that can run deep learning. We are looking at your classic, so one of the Mars helicopter. Now, the only way we could fly is if it's extremely, extremely light. So the only hardware compute avionics we could find was the Snapdragon processor, which is the same processor that runs on your mobile phone, iPhone right now. It's the Snapdragon 820. So that's the one that we will be flying to Mars. And as it turns out, it has just enough radiation that it could survive on Mars for the time that it's required for Mars helicopter. And we did that testing, and it turns out that it could fly. So yeah, we are also optimizing hardware, and we're looking at other hardware solutions that could be better for AI tools.
How would autonomous systems be applied to bots on Mars when we barely know the surface?
Um, we do know the surface to some extent because we have been driving on Mars for many years. Geologists have been studying Mars for 30 plus years. So Mars is actually relatively more known as compared to here on Earth. At the same time, we've touched only a small part of Mars, so we don't know a lot of Mars already. So yes, it's a challenge for us to basically also develop tools that can learn on its own. And these are some of the things we are currently looking at, and how can we have these unsupervised or self-supervised machine learning systems that could try to learn on its own by just experiencing. So one example of that is like trying to put some sensors on your wheel and trying to basically get feedback data on what kind of surface it is, and then trying to learn from that. That's just one example. That could be done from a lot of different ways.
Anushka asks, Deep Blue versus Kasparov made use of symbolic AI and not so much of machine learning, if she's right. What would be the difference between the two?
That's correct. So Deep Blue was definitely a good example. So it did use more of symbolic AI, but that was more of a canonical example to put in there. It did use some early parts of machine learning in very simplistic ways. It did not use deep learning, but one of the most exciting areas of machine learning that's just emerging, and I have just started a project on that. I'm personally very interested in it. It's called neurosymbolic AI. It's a combination of trying to look at a lot of the symbolic AI that was done for years, that was still a lot more rule based, and trying to use these really powerful neural networks, reinforcement learning techniques, in general deep learning that was done to solve problems like AlphaGo. Um, those are two very different kinds of two different kinds of solution space, with each having its complementary benefits. And now there is a field of neurosymbolic AI that's looking at how to combine them together to get the benefit of both. And yeah, so that's the difference, as well as the way forward. I
How
hope I
else
answered
could
those
our
questions. Yeah.
yeah, we hope so. Well, how else could our attendees reach out to you except for LinkedIn?
Um, LinkedIn would
Quite
be
a
the
few of them
best
are
way.
interested.
LinkedIn would be the best way. I had my email on the last slide. I can type it down in this. Uh, it it is hard to respond to each email personally, definitely, but I can try to if you have. So it helps to have specific questions. So if you're interested and if you have a specific question and reach out, I'll definitely try to answer as many as possible. I have just sent out my email address here on the chat window.
I think that should help out with the person said. What does NASA expect from an AI engineer as far as skills?
Um, well, a lot of the same things that you would typically from any AI engineer outside, so which would be very strong math background, very strong problem solving skills, uh, and pretty again solid foundations of programming, computer science fundamentals in general. One thing that helps and is important for NASA outside of that is experience with robotics. So one difference between working in uh, machine learning for Facebook versus machine learning for NASA is that you're not just working on your computer system. And there's a difference between working on trying to develop AI for a data set or a paper or a system like Facebook versus working on a real system. Robots, just like humans, do not behave in a predictable way. You can build your best tool and they will still have some hardware issues. So when you're trying to work with hardware, it's a completely different ball game. So having experience working on real hardware, working in the field, knowing those kinds of things is really does help you a lot. So I think a lot of that helped me get into and help have a better hand over other people who would just come from a computer science background.
All right. Would there be a possible link between hackers and space tech?
Well, can you elaborate on that? I actually don't get, I don't understand the question there.
Well, when one of our participants is interested to see if there's a chance of hackers or anything related to that to be a part of space technology or be in the said field.
Yes, it's constantly there. I mean, cybersecurity is one of the biggest challenges. I mean, even for space right now, especially when space is always a political issue. So there is always a race. Previously, it was from Russia. Now it's a global race. We have basically everybody is trying to go to Moon and Mars and beyond. And commercial companies are going, and the economy is opening up. So, how do you make sure that you stay safe and people don't use up your asset? Uh, so the classic example would be you have satellites in orbit, and some of them are spy satellites, some of them are not, and some of them could be misused uh, against you. So cybersecurity is probably one of the biggest areas that we need skills for.
Well, Zaid has asked, as CNNs are more computation heavy, aren't there any other deep learning models which could solve the problems more efficiently without a normal camera?
Yes, and that's what we don't rely only on CNNs. That's one thing we're learning from. So I had a video of Spock Light in the slide, and what we were using there is a linear SVM. So a very simple linear model that's extremely efficient to run. It's limited in what it can learn, and it's limited in how much it can do, but it it works for a limited number of cases. So if you can design your system for a specific area to work on a specific problem and constrain that problem, then yeah, you can use very simplistic model. At the same time, this is an open area. We're still trying to learn how to do this better. We're looking into model compression or even looking better into more of classical machine learning and using symbolic AI. How can we basically bring these down to compute efficient systems?
Shreyansh, could you elaborate a little more on climbing rocks and how AI was used, for example, in Lemma?
Okay, so basically the simple way we use that is for trying to predict surfaces, surface roughness, different features on the surface, which would allow us. So we had a model of the terrain and what kind of terrain would help to keep the rover on the surface versus if you basically put on certain kind of terrain, it would help it fall off. So you look at a lot of number of features like the terrain type. So if the terrain is very smooth versus if the terrain is rough, you look at the geometry of that. You compare, you take into account the robot's own dynamics as well as the center of gravity. Um, a lot of that is basically modeled together, and then you put that into a learning system, and you learn this from images directly. And there's a lot of part on the other side, like for example, on how the mechanical system is built. If you're interested, you should Google for Lemur, Lemur, NASA, and you should pretty much find videos and papers on it.
Uh, could we launch a satellite around Mars, which is having a huge computing power, and other rovers and robots in Mars that can use the same computing power as we do use in cloud computing?
Um, that's actually, if I understood the correct question correct, that uh, did did it say that could we spend like a cloud computing around Mars, like in the orbit, or could you repeat that? Sorry.
Can we launch a satellite around Mars, which is having huge computing power, and other rovers and robots on Mars that could use the same computing power as we do using cloud computing? Basically, I guess
Uh,
interlinking all of them.
yes, that's a great idea because we are studying. There is currently a project. I'm not involved in that, but we are studying exactly that idea of sending basically a big compute system that's going to be constantly orbiting around Mars, and we'll be using that sort of like a cloud on Mars to process and even for data storage.
Well, as ML requires a lot of data for good precision, seeing that we do have certain amount of data with us, but still we do again feel a lack of it. So how does NASA train models with such limited data from the Mars surface?
Well, that's again, it's a challenge from both sides. I gave you some examples of how we are trying to collect more data by using citizen science, as well as game engines and procedural development. But I'm personally approaching that problem more from a machine learning perspective, that a more fundamental perspective, that can we try to learn or build models that could learn from very sparse amount of data? So this is a very big question right now, and a lot of people are trying to figure this out. And it's a field called learning with less labels, so or zero shot learning. So this is something I'm also exploring, and my team is exploring, and we're looking at just given a few examples, can we quickly learn something? And humans are good at it, so can we teach machines to do it too?
Well, someone's asking how well is SpaceX doing according to you?
They're doing great. I mean, that's we all know. I think nothing is hidden about SpaceX, so they have been doing fantastic progress, and it's all part of um, the plan that NASA has. So oftentimes NASA is seen as, people think NASA and SpaceX are rivals. We're not. We are a team. It's almost we are a government agency. SpaceX is a commercial agency. Over the last decade, they have been part of a commercial, something we've been basically doing since the early 2010 is a commercial crew program. And in general, there is a big push of bringing commercial industry, commercial startups, commercial industry, and take over a lot of the things that NASA was doing. And this is the only way you can scale up economy. Government usually invest into things which are far out. We invest into Mars exploration when it is not economically beneficial. There is no investor who's going to invest into Mars exploration right now because there's no money coming out of it. Eventually, it will start doing, and that's where we want to start bringing in commercial companies. And this is what we did with SpaceX. Uh, Launching vehicles was extremely expensive, and we've been doing that for 30 years, 40 years with the space shuttle. We even had re-landing. We had basically SpaceX space shuttle was a reusable vehicle. It's just that we could not do it at scale because it's hard to build things without having the kind of commercial input that's coming from SpaceX. So this is where we tried to build up the ecosystems, and this is NASA's role within that. And we're trying to do that for the moon right now. We're not just going to the moon with NASA resources now. We're going to go back there with all commercial resources, with the help of all commercial partners, so that they can basically take the economy and then make business out of the moon and use it, while we try to explore more of the science questions that are for Mars and outer planets, which no business person would be doing right now.
Well, then we'll get along with our last question. What would be the role
Okay.
of reinforcement learning in future space missions?
It's an open question. I'm exploring that in a few ways that are very open right now. I don't have answers. I don't have good things to say. We are exploring that in the context of Mars rovers, navigation, as well as other areas. Uh, the challenge with reinforcement learning is it's still too early. It's a very uh, early technology. It's not matured. It doesn't even work on robots here on Earth. It only works on very toy data sets, on very specific toy problems, uh, but doesn't really scale. And what we are talking about is space exploration, which is probably the most extreme data point of mission critical, safety critical system. One error and you basically lose a $5 billion rover. So it's not something that you can take risk with. So we need to mature reinforcement learning and use it in a way that it could work with these kinds of safety critical systems. So if you have ideas on how you can use reinforcement learning for space exploration, please write to me and we can talk more about it.
Great then, Shreyansh. I guess that's it for the day. And thank you for joining us today with such an exciting session. We had a lot of fun watching you and the videos that you showed us. And it was lovely having all of you today. Thank you, Shreyansh. Thank you, my team, and everybody. Hope to see you soon at the next TCX.